time we were looking at the Neutrino problem, and we essentially looked at the experimental part of Neutrino. We saw what kind of neutrino the sun generates, and then we saw what we observed when we looked at it. And the main results were ones that came from radiochemical experiments, so chlorine or gallium. In gallium experiments, we saw that about 50% were lost. In chlorine experiments, we saw that maybe about 70% were lost. And then we looked at the water cylinder experiments, which are sensitive to 5 MeV onwards. And we can also look at a spectra. The energy range, 5 MeV to 15 MeV, half of them were lost. So, and of course, we had this heavy water experiment, which showed that if you only look at muons, they seem to be lost. But if you look at a combination of all mu as well as mu tau, then everything is counted. That is neutral current gas. And then they saw that it's quite possible that muons actually just go into the mu tau. So this is what we learned from the experiment. And what we are going to do today is to do the theory behind it. Because we know that looking at small neutrinos and their convergence is very different from that of atmospheric. Because when you have the sun, we have matter, and we saw that we have neutrinos passing through matter, everything changes. The mixing angle changes, their delta and square changes. They can go to some resonance where funny things may happen. So if you want to look at solar neutrinos, you have to look at all these complications. So what I plan to do today is to essentially go through the theory of how to handle all these complications. And in the next lecture then, we go back to the solar neutron data and use the result that we get today and see which is the right solution. So today is going to be essentially developing the theory of neutrinos propagating through matter. So before we go there, do we have any questions? Okay, fine. So we already saw that when neutrinos travel to matter of constant density, then their mixing angle changes and their attachment changes. Okay. So this is what we do. So let's see what neutrinos do when they propagate through a MSW resonance. Then we introduce the concepts of adiabaticity and flip probability. So I tell you what is flip. Neutrinos sometimes tend to flip from one ion state to another. Then we will go and look at the fate of the new bees which are produced in the core of the sun. The sun produces new bees. And then we look at this feature called as day-night asymmetry, which should give us some more features. So propagating through MSW resonance. So let's go to diversity resonance. So when we are propagating through matter, our effective Hamiltonian we have seen earlier has this key. Where this Vc is the potential due to neutron propagation, due to matter. So this Vc is root 2 Gf times Ne, where Ne is the density of electrons. There are no positrons, so now when we diagonalize this Hamiltonian, we saw that our eigenvalues look like this. So eigenvalues, if Vc was 0, then the eigenvalues would simply be, so this is 0, so this is delta cos theta whole square plus delta sin theta whole square, so that is just delta square, so that's half delta. So H is will be equal to some plus delta minus delta. Effective mixing angle look like this. Okay, again, when so Vc was 0, this would simply be tan to theta as expected. But then we saw that as we approach the resonance. Resonance means that denominator becomes equal to 0, theta will become less. So this is the resonance condition. So resonance was when delta VC by 2. So two very crucial things after this. One is that theta n becomes 45 degrees, and second is that the R square difference delta n becomes minimum. So we can actually see this by looking at this plot. Okay, so this plot has brackets. So this is the same as VC. So VC is on the x-axis. Y-axis is n square. Okay, n square simply means the eigenvalue of the Hamilton. Now let's see what happens. If you are at in vacuum, so only look at this positive place, okay, positive part of it. So if you are in vacuum, then you essentially have got your values of n square in vacuum. So this is plus delta minus delta. Right? I have not shown you where the zero is. Zero doesn't matter. What matters is the value of delta. If you go very, very far away, then what happens? So look at this Hamilton. If you go very, very far away, then this element will be very large because VC is very large. So this matrix basically looks like there is a large element here, and everything else is a small element. Small, small, small. So therefore, the largest eigenvalue is just like this big element, which is like VC. So at large VC, therefore, this particle, this eigenstate which is u2 in matter, will grow linearly with VC. So you will actually plot these eigenvalues in your assignment, and you will see that they actually take this shape. So the two eigenstates in matter are called as u1m and u2m. I use the convention that u2m is the heavier eigenstate, u1 is the lighter eigenstate. So clearly at very, very large values of VC, u2m is very high and is approximately equal to VC. Yeah.
So what are x-axis and y-axis?
X-axis is VC, which is this potential. Okay. Y-axis you can call it m square, you can call it delta m. I haven't given these scales, so I also call it delta m is m square by 2b. So m square in matrix. So you can look at y-axis as these eigenvalues. So what I am plotting here are eigenvalues as a function of VC. It's a very simple function. The function is just this function. So here you clearly see h plus and h minus as a function of VC. Quadratic function. What all I am doing is plotting that. Because finally it's useful if we talk about eigenstates property. We always talk about eigenstates in mass equal property. So usually do people get an idea of this? U2 is a mass eigenstate in matter.
So eigenvalue is a mass.
So its eigenvalue is something like this. It's like h plus. So the eigenvalue of u2m is VC by 2 plus this big square. And the eigenvalue of u1m is h minus. So VC by 2 minus this whole square. Yeah, so it depends on what eigenvalue. So this is, if you look at this Hamiltonian, that has, this is of the form delta, right? So delta m square by 2e. So dimensions of mass, but it's actually delta m square by 2e. Okay. There is a convention where people don't use the 2e factor. Okay. So then that becomes mass. That's why, see, it's only a matter of factor of 2e. So this can be written either as n square or as delta m, which is n square by 2. So it doesn't differ. If I want to put in numbers, then yes, n square by 2. So whatever you plot, the shapes will be very similar. So delta m is actually the difference between these two. And you will see that at this point of time, this difference becomes minimal. Not zero, but very minimal. So what is happening inside the sun? Inside the sun, you produce mu E. Now this mu E will compose of some linear combination of mu1m and mu2m inside matter. Okay, in the core there is some density, some DC. It is some mu1m and mu2m. These mu1m and mu2m will propagate from high density to low density. So on this plot, mu2m will start here and will propagate in this direction. mu1m will propagate in this direction. And at some point of time, they should reach the Earth in this. So what is the difference from the atmospheric case? What we did there, if you start with a mu, for example, it splits into mu1 and mu2, which I guess it's inactive. mu1 and mu2 propagate independently. They reach the detector, and again they combine and you find what fraction of that is left as mu. Now we do the same thing. Okay, again we start with mu. They split as mu1m and mu2m because in mu you have a matter. Then they will propagate to the Earth, so on, which you will see. At the Earth, again you will have some mu1m and mu2m. Then we will combine them and see what fraction of mu is going to be served. That's the idea. So, what will you do? So now we are going to look at the propagation of mu1m and mu2m. So let's try to develop the same formalism that we did before.
So you said difference is the difference between this. As you can take from, because if we put this equals to 0 there, this equation, that will be simply dead. That is on that x square axis. So at some point of this the delta square is 0. So that's the point of industrial.
Yeah. So on the way, we have seen what to do here. We have seen what to do here. Okay. But now, on the way, neutrinos will pass through this MSW resonance. Okay. And we will spend the next 10-15 minutes worrying about what to do when they pass this resonance. So that part is the question. Because remember, this is the part where delta and squares are close by and theta is very large. Extremely very large. So we have to deal with this part. Okay. So we have to talk about what we call as instantaneous mass eigenstate state. So at every point of time, when you do the propagation, we will change our basis. As long as we take care of this continuous change of basis, we are fine. So what do we do? So we define our. See, earlier, remember for vacuum eigenstates, we had mu1, mu2 is u dagger times mu. But this u dagger was negative. Only difference is now I add this matter subscript. So then u1m and mu2m is u dagger of theta m times mu and mu. Everyone knows what is u of theta m. Cos theta, sin theta, this is standard. Now we try to look at the time evolution of these states, mu1m and mu2. What to do? So let's see what we do. So I just want to take I times d by dt of the left hand side. So I times d by dt of this is I times d by dt of the right hand side. But now remember that our u is not a constant. Okay. Earlier u was a constant, so we will find. But now u is a changing parameter. So we also have to look at derivatives of u. So this is a simple expansion. No? So this is I times d by dt of this times mu plus I times keep this as it is and take d by dt of this. So simple product rule of differentiation. We will agree with this. So now let's see what we know about this. So we know how to write du dagger by dt because we know what is theta. That's all. Then we have mu, but we know that mu is the same as u times mu1 mu2. again by definition. This is important, you will agree because we are going to go a bit faster. Okay, so you will agree with this. Wonderful. Now let's look at the second term. Second term has this U diagram which I have kept the way it is. And now we worry about d by dt of mu in u. What is d by dt of mu in u? This is d by dt of mu in u is what we need. Okay. But what is d by dt of mu in u? Okay. We know that I times d by dt of mu in u is equal to h times mu in u. Okay. And of course we know that mu in u we can write in terms of u1 and u2. So this is equal to hf times u of theta m times u1 and u2. So I d by dt of mu in u is simply equal to this. So let's go back and substitute it. So I d by dt has become this. This is the I d by dt part. And it should have stayed as it. So then what we have got now is the evolution equation for mu1 m and mu2 m. So just try to write it down nicely. So I d by dt of mu1 and mu2 m. Now look at the second part. This is u dagger theta m times hf, this in favor space, times u theta m. So what does this mean? It means you had this hf and you are rotating it into the basis of mass eigency. So it becomes diagonal. So this term is actually nothing but simply equal to something like delta m minus 1. We had minus here, right? Minus delta m plus delta m. That's what we have. So we had these two terms. And this term turned out to be very, very simple. Like if you look at this carefully, this equation, if we forget about the continuous change of our basis, so if our basis is not changing continuously, just look at left hand side and the right hand side. And you will see that it's the same equation that we got for constant matter density. So d by dt of this state is just diagonal matrix times mu1 mu2.
Hamiltonian is constant.
Yeah, Hamiltonian is constant.
The matrix that transforms Hamiltonian that is this.
Right.
That contribution is constant. And one thing that amongst mu1 and mu2, which one you say is the
mu1 m is that, mu2 m is 3.
minus 1.
the absence of fluctuations in matter density, we would simply get this part, this, and this would be straightforward. So therefore, now we have to calculate this term, which will tell us what would happen when matter density fluctuates. Okay. So it's simple. So let's calculate this. So d dagger by dt is d by dt of, so u dagger is cos theta m minus sin theta m sin theta m cos theta m. So if I do du by dt of this, what do I get? Some more here. So cos theta m is minus sin theta m times theta m dot. This is minus cos theta m times theta m dot. This is again, this is simply cos theta m theta m dot. And this is minus sin theta m theta m. Okay. So now I will do du dagger by dt times u. So which is, we keep this theta m dot outside, and this du dagger by dt is minus sin theta m minus cos theta m minus sin theta m times u. So u is cos theta m sin theta m minus sin theta m is equal to theta m dot. Now we can say minus sin theta m cos theta m plus cos theta m. So 0. Then we have minus sin square minus cos square, so minus 1. And here we get plus 1 cos square plus sin square, and here again we get. So all this changing of eigenstates on the way has cost us by giving us this extra magic. So now if I want to write down the complete expression for the change of u1 and u2, this will be minus delta m minus delta m dot so this is I, this is I, sorry. So this is I. Okay, good. Solves my problem because I was worried by this looks non-permission. I say. So now what has happened now is the evolution equation that you wanted to solve has reduced down to this equation. See, theta m dot was 0, these two terms will vanish and you only have a simple equation. This is the complication that comes in. So this is the equation of evolution of instantaneous mass characteristic matter. We have to go ahead. So what does this mean? This basically means I have two different differential equations which are coupled. So this means that I have I d by dt of u1n which will involve some u2n, and similarly I d by dt of u2n which involves some u1. In general, this is difficult to solve. It is difficult to solve because theta m is a complicated twist. So remember, theta m was given through tan of 2 theta m, which had this complicated expression. Tan 2 theta m is this. So first, someone has to give you what is the value of Vc as a function of distance. Theta m dot, it would mean that you would need derivative of theta m as a function of distance. E is distance. This means first you have to know tan 2 theta m as a function of distance, which means you have to know the potential as a function of distance. And potential as a function of distance can have any form in general. For general BC, the problem is not solvable analytically. You have to do numerical. So only very special cases can our evolution equation, this one, have nice closed form solution. Everywhere else, we can approximate a solution but not really exact. So therefore, I am not going to ask you to solve these things completely. It's not possible. What we can do is we can solve this equation in certain limits, which are easy to understand. So, talking about these limits, we are talking about what's called as adiabaticity. What does adiabaticity mean? So, remember this equation. So, this is the equation. So, of course, if this and this are 0, it's very, very simple, right? So, nu1m always stays as nu1m, only its phase changes. Nu2m stays as nu2m, only its phase changes. Okay. So, if in some limits, that is a good approximation, then we are fine. So, of course, we know what is that limit. That limit is the one in which diagonal elements are much smaller as compared with the off-diagonal elements are much smaller as compared to diagonal elements. In fact, we should compare the diagonal, this off-diagonal elements to the difference in diagonal elements. So, the common factor can always be taken outside. Anything which is identity, you always take it outside. What matters is the difference in the diagonal elements. So, if we are in a situation where theta m dot is much smaller than delta m, then we are fine. Because then the situation is very, very straightforward. This condition is what's called as adiabaticity. Adiabaticity means that u1 does not know what u2 is doing, u2 doesn't know what u1 is doing. That's adiabaticity. So, yeah, so dia is the same as in this line, diaphragm separates the two. Adiabaticity means that two things are completely separate. So, if this is true, that 2 times theta dot, which is off-diagonal element, it's much smaller than 2 times delta m, which is the difference in diagonal elements, then mass iconization will travel independently. And then we know how they travel, because this we already know. There is no mixing, propagation is very, very simple. So this J stands for J can be 1 or 2, so nu1 m or nu2. Okay, so this is J equal to 1 or 2. So J1m, so nu1m will go as nu1m at 0 times this phase, which is n square by 2d. Similarly, nu2m will be n square 2m, and then we'll see later. So what this means in terms of the picture that we saw earlier, so this would mean that this nu2m line, we just carry, so all the neutrons that were produced here will simply propagate like this and come to the one. Everything that was produced here will propagate like this and come to the one. This resonance will not bother them at all, because we saw that off-diagonal elements are always small. So propagation is, to very good approximation, simply propagation of eigenstates separately. which is of course the simplest condition. That's the adiabatic. So what do you want to go to simple cases. So the most simple case is when this matrix, this Hamiltonian, is diagonal. Right? So that is theta m dot are 0. Of course, no, they won't always be 0. So let's go to the next simplest, which is that these elements are much smaller as compared to the difference in diagonal elements. Therefore, no, they are next order. So we can take another relation. Okay, but right now I can assume that these are almost 0. Therefore, mass eigenstates mu1 m and mu2m travel independently. And that's what is meant by this. So mu1 m travels in its own way, just gains this phase of n square by 2e. Similarly, mu2m also gets a phase. They get different phases, okay, but they travel independently. Because vacuum oscillations, there is no theta m dot. Okay, so it was always diagonal. You know, vacuum was simple because the propagation in terms of mass eigenstates was always diagonal. Okay, diagonal propagation is always straight. Similarly, constant matter density was easy. The next step now is varying matter density, but the rate of change of theta is very, very small. Which corresponds to saying that the rate of change of density of matter is very, very low. So we can quantify what that is. At this point, this is the simplest. So now, okay, so I was just trying to give you a pictorial view. Pictorial view says the following. So if you produce something in this eigenstate, okay, since the two eigenstates now do not mix, whatever you produce here will travel along this line and will just reach the earth. Similarly, if you produce something here, it will just reach here directly. Okay. If it was not adiabatic, it's possible that some of these mu2m will become mu1m. So that doesn't happen. The equation is the general equation like this. Some of the mu1m can become mu2m, right? Because there is some term that combines to mu. So adiabatic case that doesn't happen. mu1m always stays as mu. Now, of course, this is a very simple situation, and we know that nature will not be so kind that always we are in this situation. Adiabaticity will be broken. Okay. It's very important to study how much it is broken. To do that, we define what is called as adiabaticity parameter. The parameter is simply this divided by this. Okay. So diagonal divided by off diagonal. This is the definition. It's called as gamma. Gamma is simply the ratio of delta m divided by d theta m by d. Okay. Maybe I should. Both are backing. Okay. So this ratio should be as large as possible. The ratio is infinite, adiabaticity is perfect, and there won't be any mixing. So that is the best case scenario for us. When gamma is smaller, then we are into problems. This is something I am going to give you in homework. Okay. Because I have given a definition of gamma, which is delta m divided by theta m dot. You know how delta m varies as a function of Vc. You also know how theta m varies as a function of Vc. Okay, through tan to theta m and so on. So in principle, you can calculate how these two vary as a function of Vc. And then I will ask you to show that this is indeed equal to this factor. Let us see what this factor is. Let's assume this result for now. This factor depends on delta m square by 2e, which is standard thing we have. It depends depends on sin square 2 theta by cos 2 theta. Okay, so on mixing angle, and this depends on the rate of change of Vc with respect to x for time, same. So 1 by Vc times dVc. So what does this mean? Larger the delta n square, larger the gamma. So more chances of you being adiabatic. So large delta n squares are easily adiabatic. It's a rules of thumb that one should sort of know. At low energies, it's more likely that you can be adiabatic. Similarly, large theta is more likely that you will be adiabatic. And look at this. This means that if the rate of change of potential is large, then the universe is small, so you won't be adiabatic. So this is what we would expect anyway. Right? So fast varying potential means non-adiabatic behavior. Very slowly varying potential is adiabatic behavior. So if we really want adiabaticity everywhere for the neutrinos, we should demand that this parameter gamma is much greater than 1 throughout the propagation, okay? Right from the start all the way in the only in that case can we use this according to the adiabaticity, not other. Right. So this is the quantity therefore that will now interest us. Okay. So here actually this result just definition of it. X is like time, so it is distance. So I use x and time interchangeably. X, distance, L, time, everything tells the speed of light. So this RES should be there. So at some point of time, you will calculate this by yourself. So now, let's talk about what is this value of gamma along the propagation of these neutrinos. So first thing you want to see is the following. See, we want this gamma to be large everywhere. So you have to find that point where it is minimum. And if the minimum value is very large, we are safe. So you have to find that value where this is going to be minimum. So look at this. Immediately came to obvious. Let me say from this. Yeah. So actually we can look at it. Gamma is the ratio of these two. Now delta n is the mass square difference, and we know that when we are at resonance, that is the minimum. Okay, so that's one thing we know. So therefore, gamma is in danger of changing, danger of being very, very small if you are near resonance. If you are near resonance, delta n is very small. So therefore, one always looks at what is called as gamma resonance. Gamma resonance is simply this same value, but calculated resonance. Yeah, so okay, so actually the expression is the expression at resonance. I should have given you more general expression, which is what I will ask to calculate. Okay. That will reduce down to this at resonance. Okay. So the minimum value of gamma is what is relevant, and that is actually is this. So what we will do therefore is the following. Whenever we come across a problem, we look at what is the value of this gamma at resonance. And if that value is large, we are safe. If that is not large, we will have to do something. That's what all the problems do. because if it is anyway large, we don't have to care. So therefore, this gamma rays is somehow taken as a measure of diabeticity rate. Given the problem, if you will talk about it, we will talk about what is gamma rays. The answer will be given in terms of this gamma rays. On the other hand, if you go very away from the resonance, note that if you go deep inside matter, theta m becomes negligible. So sin square root theta m becomes equal to 0. Right? This you remember. Tan theta m depends on. At large matter densities, therefore theta m is 0. So sin negligible. So sin to theta m is equal to 0. So therefore, this gamma, which has sin square to theta on top, will be 0. Actually, I am giving you some wrong value, so let's not worry about it. This argument has a problem. No, that's because I did not use the correct expression for resonance. The expression here is valid only at resonance, but further away from the expression is different. Maybe perhaps I would be calculating. That might be a good expression. So this gamma was not entirely divided by formula. Let me see if I can do it online. If I cannot do it, then let me see if I have all the information right now. So this is data m square in measure divided by V. And now I want to see if I can really write down d theta m by dt in the expression. Let's see if I can do it without anything. So how will I do it? The good thing actually is to use the relation says that delta is equal to vector times sin theta m equal to theta m square okay. So I didn't tell you this trick before, so let me show it to you. Okay. So remember what we had got. So we had got delta m was square root of delta cos theta minus this is got it right. Plus delta sin theta whole square. Okay, this was of delta. And then we also calculated sin square theta. This is something that we wrote down before. Was delta sin theta whole square divided by these two expressions were similar here. So from these two, you can see that this is 2, right? So this is like delta m. Delta m times sin 2 theta m is the same as delta m square. So this is just some. some relation. Now this might help me calculate my P theta in my T. So let me see if I can. I'm going to do some complicated things. Derivative of BC and so on. So let me not go into it. That will take too much time to do. So right now, forget about this. Okay. So I'll give you some maybe the assignment I was going to show. And away from the resonance, diabeticity will always hold. Intuitively, one can see this in some sense we are the following. The reason that you are allowed to jump across these eigenstates at resonance is because the eigenvalues come very close to me. And then uncertainty principle allows you to be able to go from one eigenvalue to another. If two eigenvalues are very, very far apart, then it's difficult for you to jump from here to here. Because uncertainty principle doesn't allow you to change the eigenvalue. So anyway, so what this means is that if at all there is any danger of breaking of adiabaticity, it's going to be near the resonance. Breaking of adiabaticity means non-adiabatic area. Yeah, these are used interchangeably. Non-adiabaticity, breaking of adiabaticity, or small gap. So as I told you, the two coupled differential equations are very difficult to solve. Can't be solved exactly. What these two people did, they found out a solution for this interchange, for this so-called flip probability. Flip probability means that you go from nu1m to nu2m at resonance. So in other words, if you have resonance like this here, something which travels along this line will now jump and start traveling along this line. The fraction of time this happens is called as TF. It's called as the flip probability. It means you flip your eigenvalue. When you flip, you become nu1m. If you are nu1m, you become nu2. So the expression for PF in general looks something like this. It looks like this also for some very special cases. It's not always true. But simple profiles like exponential, power law, and so on, these people calculated what the value of PF is, and then they wrote that in terms of this. So let's see what the parameters here is. It's exponential of pi by 2, gamma resonance. See, people use gamma resonance because it's a good quantity to measure. So you look at a problem, you calculate what is gamma resonance. There is this factor called as F. F actually depends on what is the density profile exactly. So there will be a table which tells you exponential if is this, linear if is this, 1 by r square if is this. But anyway, the expression becomes complicated. Okay, that's the reason. So we will never try to derive this, okay, but I will give you the reference to this paper. Those who are interested can go here. They have tried solving this problem for many different profiles, and then they give you the table of this. What we are interested in is the sun. It so happens that for the sun, F is approximately equal to 1. So therefore, the expression becomes slightly simple. Second nice thing that happens is that we are interested really in two different limits. One is that gamma resonance is much smaller than 1, and second is gamma resonance is much greater than 1. I think I interchanged this. So this is gamma resonance much smaller than 1. This is incorrect. This is actually gamma resonance. gamma resonance much greater than 1, this expression begins to this will saturate this. Yes, gamma resonance will much greater than 1. It's adiabatic, almost adiabatic. So in that limit, this is the true state. Okay. So which you can check. So we take the limit of this expression, so put it equal to 1, and look at what happens when gamma res is much greater than 1. And then you will find that PF reduces simply to this expression, which is exponential of minus pi times gamma res. So way to look at it is the following. Look at this numerator. Okay. Now this is a large quantity, exponential of minus pi over gamma res by f. Okay. There is a 1 over sine square theta here. So this quantity therefore will be much larger than the earlier quantity. So this will dominate and this will stay the way it is. Similarly in the denominator, this quantity is much larger. Therefore exponential of this quantity is going to be almost 0. So denominator is going to be equal to 1. Okay. So PF therefore will be simply exponential of this quantity if gamma s is much greater than 1. So the argument is more value for theta square. Okay. However, even if theta is large, sine square theta is always less than 1. Okay. So it's like e to the power x, where e to the power minus x, where x is very large, and e to the power minus 2x, for example. Okay. E to the power minus x is always much larger than e to the power minus 2x. So theta small is sort of more correct. So 2 times the But even when theta is not very small, the approximation is reasonable. On the other hand, if you are going to talk about gamma is much greater than 1, then we have to, I'm sorry, what should I check here also? Each over here. It's much less than 1, then again we have to expand this, and then you will see that this reduces only to cosine square. You quickly see it, it's not like it. So what do you want to do? So your gamma is much less than 1. Then we have what? Exponential of minus pi by 2. I won't write this. It's pi by 2 gamma minus exponential of minus pi by 2 gamma by sine square theta. So minus pi by 2 gamma. So pi by 2 gamma I call is x. So we got exponent of minus x minus exponent of minus x by sine square theta divided by 1 minus exponential of minus x is small, so I can expand, and this becomes 1 minus x minus 1 plus x by sine square theta. X is small. So divided by 1 minus 1 plus x by sine square. So if I am not anything wrong, we get equal to 1 cancel, all x's cancel, so minus 1 plus 1 by sine square theta divided by plus So this complicated expression boils down to cosine square theta when gamma rays is much smaller than. So these two are things to keep in mind. So after all this mess, what do we get? We get that if things are sort of adiabatic, then PF is given by this. If they are very non-adiabatic, PF is simply cosine square. So when we talk about the solution to the solar problem, we basically talk about only these two things. Details are this gamma rays will depend on energy. Apart from delta n square, theta, and metal profile, this will depend on energy. So that is the PF therefore will almost always depend on energy. So now let's see what happens with UVs that start from the sun. Okay, let's start from UV. So firstly, inside the sun, you only produce UV. Okay. We know that deep inside the core, theta n is 90 degrees. What does that mean? That means that UV is equal to mu2. U2m. People agree with this? Okay, so remember we had this U is cos theta times U1 plus theta times U e equal to U e, let me just tell you, I think this was cos theta n times U1 n plus sin theta n U2. And if theta m is 90 degrees, it means that UV is basically equal to U2. So inside the sun, therefore, all the UVs always start as U2. There is no U1. So our job is simple. So you have to start only with this U2 at a corner. So inside the sun, you basically start at this point. You will have nothing, it starts from here. All UVs will start from this point. So all we need to care is when these UVs travel along this line, whether they jump here or don't jump. So not a mass eigency. So you talk about mass of UV. However, deep inside the core, UV becomes a mass eigency because it is the same as UV. See, because of this fact that UV is the same as UV is why we can say that deep inside the core, UV has a mass. That's because it is the same as the mass of this UV. So now this UV starts at mu2m. This mu2m keeps on propagating till mu2m keeps on propagating till you reach the resonance. At the resonance, you somehow solve this coupled differential equations. It will tell you what happens to this UV after the resonance. So let me write down the general statements. What happens to UV after resonance? After resonance, it becomes some amplitude times some phase times mu1m, and some amplitude times some phase times mu2. Okay. And amplitude are arranged such that if there is no flip, then everything is only mu2m. If there is flip, then there is some mu1. So mu1 fraction is like PF, mu2 fraction is like 1 minus. So mu2m has started propagating. After the resonance, it converted into a combination of mu1m and mu2m in general. Okay. with probability Pf it became nu1m. With probability 1 minus Pf it stayed as nu2m. So in general I can write it like this. Its amplitude, so root Pf times some phase times nu1m plus root 1 minus Pf times some phase times nu2m. That's what it became. We are right now parameterizing it and not calculating Pf and chi1, chi2. It's just something to give us. Okay. So this is what happens when they come out of the resonance. After the resonance, they will just travel to the earth. Okay, because after resonance, they won't interconnect. Then what happens? The nu1m part just changes by phase by nu1m times this exponential. Standard phase difference. Nu2m will also travel, but will travel with this phase. When you get m square 2n by. And finally you reach the earth. So what you are doing is exactly what we did for atmospheric neutrinos. We did not involve this complicated state of root Pf and nu1 versus root 1 minus. Otherwise things are exactly the same. So you produce nu1m and nu2m and they propagate. And finally when you come to the earth, you try to compute this quantity, Pe. Pe means you start with μe, end with mu. How do you calculate this? You take inner product of μe with mu of t, which is this, and then you take its mod square. Then, so how much is that? So mu t is given by this, and we know what is mu e. Mu e is cos theta times nu1m plus sin theta times nu2. So now we can do this. So we highlight the mu e. Equals cos theta. See, at the earth, see, once we reach the earth, you basically are exactly. Cos theta times nu1 plus sin theta. M is the same as nu2 and nu1 is the same. So this will give you Pf times cosine square theta. This term will give you 1 minus Pf times with nu2m, so sine square theta. And then you have got a cross term. The cross term will be root Pf times root 1 minus Pf times cosine of this chi1, chi2, and the phase difference between these two. Mod square, no? Nu e times nu t. So okay, yeah. Alright? Yeah. So you calculate nu e nu t inner product, which will be root Pf times nu e times nu t. This will be some root Pf times e to the power I chi1 times cos theta and something is exponential. Blah blah blah. Plus we have 1 minus Pf power I chi2 sin theta exponential. So you square it, you get Pf cos square theta